Hello and welcome back. As I promised, we're going to talk about SN1 reactions, and I think I'm going to do SN1 reactions in a green pen. SN1. So again, S equals substitution, N equals nucleophilic, nucleophilic, and this time our 1 is going to equal unimolecular. So on the last video where we talked about nucleophiles and substrates, remember how I said a secondary group leaving group will react with a nucleophile, can react with a nucleophile, and react, I'll just call it R1, R2, R3, and what we will see is that R1 and we'll have an inversion, right? This is via SN2. What we notice though is when we have a tertiary, so a secondary will react via SN2, and we'll talk later about how to determine if something is going to be SN2 or SN1. But when we have a tertiary, so I'm going to put a methyl here, I'll put an ethyl here, and there you go, something else there, and I'll make my leaving group LG. So I clearly have a chiral molecule. When I react with my nucleophile, my product will be, put my little methyl, ethyl, boom, 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 and my nucleophile, but I will get a racemic mixture. So I will get both this compound and I'll also get this compound. So what that tells me, is that I will have a racemic mixture. So remember, SN2, we went with specificity. We inverted that stereocenter. Something about this SN1 reaction, it's clearly not SN2 because we do not have stereospecificity. This has a lot more steric hindrance, and there's a lot of things that make it hard for the nucleophile to get in. So there's going to be a different mechanism. In addition to that, let's talk a little bit about the rates. If I have a concentration of one of my substrate, one of my nucleophile, my rate will be 1. If I double my substrate and keep my nucleophile as it is, my rate will double. If I keep my substrate the same, double the nucleophile, my rate remains at 1. And if I double both of them, I only double my rate. This tells me that the thing that is dependent on the rate is actually only my substrate. That's the only part of the reaction that governs the rate. So let's quickly go over this mechanism, and then I'm gonna put these out for you guys to work on a little bit and just digest the SN1. So what's going on in an SN1 reaction? It cannot be a one-step concerted reaction. If it were that, we'd have we would have an enantiomerically pure product. So let's again look at our structure here, and I will make it enantiomerically pure. And this time I'm going to make it an I, just because that's a good leaving group. So now, and for the nucleophile, I'm actually this time going to use methanol. So CH3OH. What's going to happen in this reaction? It doesn't matter. Notice this isn't a good nucleophile, but this reaction will go forward and it will give me the two different products eventually of OCH3 and color OCH3. Notice that this is different than water or sodium hydroxide. I don't have the OH. I keep my carbon-oxygen bond is much stronger than the carbon-hydrogen bond. So what's going on? I don't need as good a nucleophile. This is still a nucleophile, right? This is still a nucleophile. It's just not as good a nucleophile, which means that my substrate has got to be a lot juicier and wanting a nucleophile more. What happens is, first things first, it's going to be a two-step reaction. My leaving group is going to leave. Boom. Now, if you notice, here's my cation. This is achiral because it's sp2 hybridized, because I'm only bound to three things. And this is my intermediate. So I have an achiral intermediate. Now my nucleophile, even though he's not the world's best nucleophile, he can still help somebody out. We still have lone pairs and things like that. Boom. And we're just going to go him, and I'll just do it this way. OCH3. And we have our hydrogen, so that's plus. And then we'll do proton transfer either through HI or through methanol. We're just going to do proton transfer. And we'll just show it through the methanol. OH. That's going to grab the proton, boom, boom. And then finally, we wind up with the product that we've wanted all along. OCH3. Okay. So that's the difference between SN1, SN2. SN1, this is my rate limiting step. I need to have that leaving group leave. Nothing happens if that leaving group doesn't leave. So when I look at my pieces for an SN1, I need a very good leaving group. I need a substrate that can make a stable carbocation. Stable carbocation. The nucleophile isn't as important, but I need an okay nucleophile. So notice how with SN1, this isn't the world's best nucleophile, but because I generated a carbocation, he suddenly becomes Prince Charming of nucleophiles and goes and attacks. And also notice if I were trying to get this reaction to happen without a good leaving group, nothing would happen. Because I need a leaving group that's willing to leave on its own. We'll talk a lot more about SN1 next class. Ultimately, the products are going to be very similar to SN2. The only difference is because I have this achiral intermediate, I will not form an enantiomerically pure product. One other thing I kind of want to show you before I leave you for today is kind of that reaction energy diagram, where here's the reaction, and this is for SN1. We start off, right, with our product, a huge energy to get the leaving group to leave, and we have an intermediate here. Then a lot less of an energy to get our nucleophile to attack, and there we go. And if you also notice, once I get to this point, I don't have a good leaving group. This will not do SN1. I would have to protonate it again to turn it into a good leaving group. That is it for this introductory to SN1, and I will see you all in class.